Okay, so what we will learn in this chapter is as follows. So if you recall, the first initial chapter of the waves over here, in which we learned about the properties. Okay. So sound is basically a type of wave which is longitudinal, right? It is a longitudinal type of waves, right? And it is also a progressive wave since it transfers energy from one point to another point, right? We have learned this also. And it follows the formula which we have basically learned before. You can find the speed of sound, usually basically two formulas. That is 2d upon t. You will learn this method कैसे करते हैं. Or you can find using the simple formula which we know, that is distance over time, right? This method will be called basically echo method, right? We'll be using echo method to basically find speed of sound in air, right? And this is the normal traditional method over here, which we have learned in our theory, right? It is a traditional method. Traditional method. Okay, so इसके अलावा if you recall, the speed of sound in air is usually around, एक मिनट रुकें, in air, speed of sound in air of sound is basically around 330 meter per second roughly, right? So we will learn all of these properties, ke, how does sound speed varies in different states of matter. We will also learn that how do we produce sound waves, right? Again, the very important question over here, ki how do we produce sound waves here, right? Okay, and so on and so forth. So let's start with the production of the sound waves over here, that how can we produce sound waves here. So if you recall, musical bands or musical instruments or someone singing in your, let's say, in your room, or some singer in a concert over here. So it basically is doing what? Let me just draw a diagram here. Let me just say, okay, this is, let's say, Hamza. Okay, Hamza is speaking to, let's say, his friend Ali, right? They're speaking about, let's say, current Champions Trophy about in Pakistan. Okay. So when Hamza is speaking, let's say Hamza says, yo man. Okay, yo man, how are you? Right. So what is happening over here? So surrounding Hamza and Ali, they have air, right? Air has particles which contain different type of atoms. So when Hamza speaks, basically causes vibration of particles, and basically sound waves travel through rarefactions and compressions and to his basically Ali's air, right? And Ali's air basically has an air drum. If you recall, inside the air, we have a very thin sort of layer which basically acts as air drum. And when the sound waves hit our eardrums, it basically vibrates. And as you, let's say, as I'm speaking right now, and your speaker is giving us the sound waves, right? And that sound wave enter your basically ears, and your eardrum vibrates. Your eardrum converts the sound waves into electrical signals so that your brain can translate it, right? Let's say if I was speaking Chinese right now, and if you don't know how to basically understand Chinese, your eardrum would be still vibrating, but those electrical signals won't be able to translate into the language which you can understand, right? That's how sound propagation works, right? So I have a question for you guys. Let's say if we go outside Earth in space, right? If I go to space, this is sun here, right? And let's say this is Mother Earth. This is Mother Earth here, right? Let's say if Mashal is basically here, let's say. Or let me just say Maeve, right? Maeve is here. So if, let's say, Maeve shouts for help from this particular point to Earth, would her sound waves travel through the space? If you recall, space has vacuum, right? It has no particles. It has no air particles. So would the sound of Maeve travel back to the Earth? I have comments here. Okay, Vardha has a sore throat. Vardha get well soon. And Maeve, perfect. Sound waves are created by object vibrating. Perfect, right? So I have a question now for you guys. Ki if, let's say, Maeve is here and if she's shouting for help to back to Earth, would her sound waves travel back to Earth through vacuum? Yes or no? If you're saying yes, raise your hands. Okay. ओके, सो मर्दा इज सेइंग कि सर मेव की आवाज हमारे पास स्पेस से अर्थ में वापस जाएगी। ओके, ठीक है। व्हाट अबाउट अदर्स? ठीक है। सो इट वुड नॉट, राइट? बिकॉज वर्दा, साउंड नीड्स पार्टिकल टू मूव। साउंड वेव्स नीड्स पार्टिकल्स टू मूव, राइट? ठीक है। साउंड वेव्स ऑलवेज नीड पार्टिकल्स टू मूव हेयर। यहाँ पे इन अर्थ वी हैव एयर पार्टिकल्स, सो एयर पार्टिकल्स. Okay, it was by accident. So air particles basically in over here in this case when Hamza and Ali are talking with each other, so sound waves are traveling through air particles here. यहाँ पे we have vacuum. So what is vacuum? So if you extract all of the air out, right? So it is basically extracting all of the air out, right? So you have no particle which are available for basically sound waves to travel through, and therefore, if any blast occurs in space, if any big blast occurs in space, you just see the light waves produce, not the sound, right? Okay, so this is one of the fact K sound waves always need something vibrating to basically produce. Okay. Sources of sound all have some vibrating parts, right? Let's say if you recall a guitar, okay, if you recall guitar and if you have played a guitar, you see that it has strings over here, right? And when these strings vibrate, you have sort of a sort of chamber inside this, which basically amplifies the sound when it a sound and basically sends it outwards. Okay. So if you see this guitar string over here, it's vibrating, right? So we can summarize this: कि any vibrating source, any vibrating source is the source of sound, right? So anything which is vibrating, let's say if you take a let's say a fork, right? And if you hit it if you hit it with with the let's say with the wall strongly, it will produce sound for some time, right? Because it vibrates and then stops, right? So if you recall, basically, let's say a flute, right? So you're throwing in air inside the flute, which basically cause the sound to be produced, right? So a drum, right? A drum basically made of a animal skin here, right? So what happens? We basically strike on the drum skin, right? So what happens? The drum top layer starts to vibrate and produces sound waves, right? Human voice has vocal cords, right? Let's say I'm speaking right now, we can hear my voice to be pretty loud, right? Loud means it has high amplitude. If a girl is speaking over here, she might have a sharp noise, right? So it depends upon. So we had different vocal cords, right, which we can hit. The singers can basically hit sharp notes and basically loud notes also, right? So we have again, we have our sort of vibrating source, which are basically coming from our basically mouths, which basically produces sound waves. It disturbs the air particles around us, and it basically leads to production of sound waves. Okay? And the sound travels through air to our ears, and we hear it, right? We just discussed it out over here. So, now this example over here. Okay, if you basically have a ringing bell over here, right? So this is a glass jar over here. It is just to show that if you don't have any air particles, you won't be able to hear sound, right? So यहाँ पे पहले initially it was air, but we are basically have a vacuum pump over here, which is extracting all the air out, right? Just to basically experience here, would sound be produced if there is vacuum inside this glass jar or not, right? So this is a circuit over here. We have a battery connected to this particular part, and this is a bell over here, right? So when the bell is out, sorry, when the air is out of the glass jar, okay, when we have no air here, so this bell keeps on ringing, but you don't hear any sound, right? Because the vibration produced here cannot be transferred, right? Because it needs medium to transfer, right? Since there is no medium here, there is no air here, so sound यहाँ से यहाँ तक पहुंच नहीं पाता बाहर, ठीक है? So this is how we can prove that sound always needs a material to transfer, right? So I hope it makes sense, right? If it makes sense till now, give me a thumbs up. Okay, it makes sense to me. Varda. Hamza, are you here? Hamza. Okay. So this is just written over here, summary of what we have discussed over here. Okay, if we pump out the air in the glass jar, so which is containing a ringing bell, okay, the bell is continuously ringing. It should be basically makes sense. Okay, we should be hearing sound, but since there is no air, the sound disappears, right? So we can also still see that the bell is continuously ringing. ठीक है तो जो हमारे पास छोटी सी नॉब होती है which continuously hits the gong sort of which produces the sound waves. ठीक है. So again sound cannot travel through vacuum as light can, right? So a medium is needed to transmit sound waves. In addition we can transfer sound through air, solids and liquids. ठीक है, at different speeds, right? So we learned this how what is the speed of sound in air, what is the speed of sound in liquid, what is the speed of sound in solid, right? Okay, so now we have learned about the production of sound waves. Now this is just to learn about the nature of the wave, right? So what type of wave is produced? See what type of wave is sound wave, right? So we have already discussed it multiple times from the initial chapters that sound waves is an example of a longitudinal wave over here, right? Right. So what is a longitudinal wave? If you recall, can you explain what is a longitudinal wave? We have done this multiple times. What is a longitudinal wave? Hmm. If you recall a spring, if you recall a spring, and this is the mass here. If you extract, basically apply force to the spring and leave it, how would the spring basically be moving over here? It would be basically moving like this, right? Sometimes here, sometimes like this, sometimes like this, right? It would basically transfer energy in forms of compressions and rarefaction, right? This is a compression here, this is a compression here, this is a compression here, and these are basically rarefactions here, right? Okay. So basically, when the and you can see that the energy is transferred through this in this part in this direction over here, and the particles of the spring are basically just vibrating in this direction, right? So this is the particle motion direction over here. This is the particle motion direction over here, right? And the energy motion is also parallel to each over here, right? So when the particle motion, so when the particle motion is parallel to the energy direction, to the energy direction, okay? So then this type of wave is called a longitudinal. It is called a longitudinal wave, right? Longitudinal. Okay. So this is, I hope it makes sense. It's just a summary of what we have done over in the last class. Last classes over here. In the last chapter, we learned that progressive longitudinal wave is basically the wave in which the particles are transmitting medium vibrate back and forth. So you can see that they're vibrating back and forth over here. Right? अभी वेव का जो एनर्जी फ्लो हो रहा है वो भी सेम डायरेक्शन में हो रहा है हमारे पास सो द डायरेक्शन इज पैरेलल टू ईच अदर सो दिस टाइप ऑफ वेव इज कॉल्ड द longitudinal wave over here, right? So in a sound wave the particles always travel through a set of compressions and rarefactions over here, right? We have learned this compression and rarefaction in the last classes over here. So can anyone explain what is compression? What is the compression? We had done this, we had defined this formally also in our last classes. Can anyone explain what are these? Hmm. Yes. Anyone? Compression and rarefaction क्या होते हैं भाई? We had done this in the last class. I want someone to explain this. Hmm. Maeve, what is the compression in a sound wave? ओके जी, आई बिलीव कि आप सब भूल गए. ऑलवेज स्टार्ट रिवाइजिंग, ठीक है. सो ये मैं लिटरली इन लास्ट 2 वीक्स बिफोर किया आप लोगों ने, ठीक है. ओके. सो let me tell you guys over here. Okay, let's say if a person A is speaking here, right? If a person A is speaking here, and let's say this is person B, this person B here, this is person A here. So when the person A speaks, so basically he transmits sound waves. Sound waves always transmits through this set of waves. Okay, so you can see multiple things here. Okay, I have answer from Vardha. Kisa compression is an area with high energy in a sound wave, and the rarefaction is with low energy. Okay, that's good, right? I thank God that someone remembers the definition here, right? So you can see different sections here, right? So the I'm gonna highlight the rarefaction with with the blue one, right? And I'm going to highlight the compressions with the yellow one, right? Okay, so this set of yellow ones where the particles are pretty close to each other are basically called as compressions, and the ones which are basically far away from each other are basically called as rarefactions here, right? So we have two definitions here, compressions. This comes in your exams, right? So don't just miss it out. They ask for definitions of these terms. So it is an area, it is a region where particles are closer to each other and have a higher air pressure, right? But they're pretty compact together. They have very small area, okay? And if you're applying the same force over a smaller area, you have greater pressure, right? So they're closer to each other over here, okay? So let me just now explain for rarefaction. It's just the opposite for that. If you know compression, you should know rarefaction, right? So now let's start rarefaction. So it is a region where the air particles are further away from each other and have lower pressure. Right? So these are definitions which you should learn. These are of 2 marks which they can come take in your exams. So I hope it makes sense here, right? So we have learned okay, now okay, how do we represent a sound wave? Okay? So it is represented using a longitudinal set of waves and it has set of compressions and rarefactions. So sound wave is transferred through a set of compressions and rarefaction, right? And if I want to find a wavelength for this particular sound wave, so a wavelength can be from one compression to another compression. This is one wavelength, one lambda, or it can be from one rarefaction to another rarefaction, right? So this is the rule for finding wavelengths in sound waves here, right? I hope it makes sense now. So if it is clear till now, give me a thumbs up. Okay, good. So yeah, so now just a definition about compressions and rarefactions. We have already discussed this in the last class. I just want to quickly go through this again. So a sound wave is produced, let's say, from loudspeaker, right? So it consists of a train. Train means कि it is a set of continuous compressions and rarefactions, right? So यहाँ पे लोगों ने बता भी दिया आपको कि compressions क्या होती हैं. Air particles are closer to each other. Rarefactions are basically molecules are further away, which we have already defined, right? Atmospheric air pressure. which is basically higher in compression and lower in reflection, right? So we have already defined it, just a summary over here. So this is how you basically represent a sound wave that is passing through a loudspeaker, right? You can understand that particles, let's say a particle A is over here, right? If I talk about this diagram, so if you have particle A here, let's say, so particle A is only vibrating back and forth in this direction, right? Particles move नहीं करते इसके अंदर, ठीक है? They only vibrate left and right, ठीक है? By remaining in the fixed position, they transfer the energy through to another particle, right? You can see कि wave की energy is also moving in this direction, right? And again, you can see that the direction of wave energy and the direction of motion of the particles are parallel to each other, and hence they are called the longitudinal waves over here, right? So that's how we basically understand the transmission of sound waves. Okay, I hope it makes sense. So let's move on. Limits of audibility, right? So now this is now we're gonna start some methods for numerical methods for calculating speed of sounds. So before that, we just need to know कि आपके MCQs में दमादम आते हैं, ठीक है? कि what is the limit of sound audibility of basically for a human being? So what do I mean by that? It is basically the sound waves with frequencies which can be heard by a normal human. Not a normal, I would say average human. Okay. I'm including case someone might have some hearing issues. So I'm just saying an average, right? This is for every human over here, right? An average human. So these are the sound waves, these frequencies, which are audible, right? Which are audible to a human, right? To the ears of the human, right? So if you recall, the frequency range which are audible to the human beings are from 20 hertz to 20,000 hertz, right? And if we have sounds which are less than 20 hertz, okay, if we have sound which are less than 20 hertz, they're called infrasonic sounds, right? Infrasonic sounds, okay, and which are again not audible, right? We cannot basically hear them, so they are inaudible, right? You cannot hear the sounds over here. Again, if we have frequencies of sounds which are greater than 20 kilohertz, okay, which are greater than 20 kilohertz, okay, 20,000 hertz, they're called ultrasonic sounds, right? Ultrasonic sounds. And again, we cannot hear them, right? They are again inaudible. Okay. So these are the range which are basically physically implied to our human beings. Okay, we can hear these sounds over here. If you recall, sitting in your let's say lying in your room, if you have a pendulum clock which goes tick 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 tick, right? It has a frequency which is pretty close to 20 hertz, right? Okay. But if you're basically, let's say if you have guests in your houses and if it is the morning time in your house and everyone is basically creating, let's say, busy in their activities, let's say your little brother is playing video games, there is noise in your rooms, you cannot hear the sound of the pendulum clock. Okay. But if you are lying in your room at around 2 a.m. and everything is pretty, when there is no noise, so you can hear the sounds of your pendulum clock, right? So again, that lies near to 20 hertz frequency. So that is how you can basically hear it, right? Similarly, if you try to hear, there are YouTube videos where we have video basically sounds of greater than 20 kilohertz. Don't try to listen to them. Okay, so that might destroy your ears. Okay, so they are basically sounds of frequencies 7,000 hertz also, right? You can try these sounds. This will basically produce a very bad effect on your eardrums, but still you'll be able to hear it. Right? But it will be simply noise and noise and noise. Okay. So again, the greater the frequency, the sharper it becomes. Okay. The sharper means that it will become very sort of unpleasant to your ears. Okay. So if you hit 20,000, let's say 19,000 hertz, still you will hear it. But again, this might lead to some damages over here, right? So these are found through experiments, the range. So don't test it out through YouTube videos. Okay. So I hope it makes sense, right? So frequencies within these range are audible to our normal human being, right? So if it makes sense, give me a thumbs up. If it makes sense till now, give me a thumbs up. Hanji, so now we're starting the properties, basically the phenomena which can occur in sound wave. So we have learned that all the type of waves can basically undergo reflection, reflection, and diffraction, right? So that is true for all of the type of waves which we have learned till now. Okay, so now I'm gonna see are they applicable to sound waves also, right? So we're gonna learn the first phenomena which is called reflection. So let me just quickly ask a question. What is reflection? What is reflection of a wave? Hamza, what is reflection of a wave? We have done this multiple times now. I want an answer, quick answer. Hamza? Hello,
सर
Hamza.
आवाज आ रही है।
Yes, आवाज आ रही है.
सर, जैसे अगर आप एम्प्टी रूम में जाओ जहाँ पर कोई सरफेस नहीं है, ज्यादा बिल्कुल फ्लैट वॉल्स हैं, उसमें
Mhm.
अगर आप कोई साउंड निकालोगे ना तो वो साउंड आप कहते हैं रिफ्लेक्ट होके वापस भी आएगी आपके पास।
Good. So if I just want to ask you, Hamza, just what is reflection? Just a generic definition.
सर, जिस डायरेक्शन में लाइक हम कहते हैं किसी सरफेस पे लाइक जा रही है साउंड वेव, उसी डायरेक्शन में रिफ्लेक्ट होके वापस आ जाए।
So what is reflection? Reflect तो बोल दिया आपने. It is the bouncing of the wave, right? From
यस
hard surface. Yeah, that's good. That's good, right? So you might have basically experienced the scenarios if you, let's say, went to an empty apartment or an empty room, right? Where you have only sharp walls, right? Straight walls. So if we speak up, you basically start to hear your sound twice, right? Okay. But if you have a huge hall that is empty, that effect might double, right? So it also depends upon the number of walls, right? So the sharpness of the wall also, right? So imagine if you go to a valley also, let's say in North Pakistan, okay, where you have almost no population and you have basically a sharp mountain in front of you, right? So when you shout, so after some time you also hear back your sound back, right? So there is some phenomena happening here, right? So what is that? So let me just start picturing a scenario here. So let's say this is a valley here. Let me draw a valley here, a mountainous region like this. Let's say, and then we have another mountain here, right? And let's say this is Varda here, right? Varda is basically standing, let's say, in the northern area region. He wants to basically see that if physics works, right? And this is again hard rocks material over here, right? We have hard rocks here, rocks here, okay, and rocks here. And let me just make some clouds here also. It's let's say a night time, right? And she basically shouts her name, right? So when she shouts her name, let's say it basically goes in compressions and reflections, compressions and reflections, compressions, you can't reflection. It basically hits this particular boundary here, right? So if I just draw a single ray to represent the direction of waves, this is one ray, right? So it basically goes back and after some time it basically comes back, right? So if I just dictate, if I just say, okay, guys, from this particular point to the point of hitting the mountain is basically distance d, right? It is distance d. And you but they also have a stopwatch. Okay. She also have a stopwatch just to basically measure time, right? Okay. So I can also set up some experiments to also find the speed of sound in air, right? Experimentally, kitni aati hai hamare paas, right? So this is this one setup over here, right? So this bouncing of the wave from the mountain and back to Varda over here is called echo, right? And echo is just one of the property of reflection here, right? So if you just want to summarize, you can say that reflections in sound waves are called echo over here, right? So what are basically this? Let's start this formally now. So sound waves are reflected well from hard, flat surfaces such as walls or cliffs. and they obey the same law of reflection as of light. All right. So the reflected sound from the echo, an echo is the reflection of a sound wave, right? So basically, if you call about reflection of sound wave, it is called echo, right? So if the reflecting surface is near than 15 meter, take care of the sound from the source of the sound, the echo joins up and with the original sound, which basically seems to be prolonged, right? Have you heard about reverbed songs? If yes, give me a thumbs up. Reverbed songs. Yes. Yeah. ठीक है. So these are basically properties of echoes जो लोग basically follow कर रहे होते हैं. They basically try to mix up the, if let's say if a person, if I'm speaking right now at a normal speed, not at a normal sort of accent, so if I add up, let's say if I create a copy of my voice, ठीक है, and if I let my voice and my copy, I add my sort of a copied version of my voice at the same time. So we'll see that my voice is sort of reverb, right? Because there will be some delay in my copy sort of part to speak up. So there will be some sort of cozy effort which you will hear, okay? So that are sort of reverb songs, right? So again, it is basically used in cinemas also. Okay, if you basically go to concert halls or cinema, so the sound effects which they have in the cinema, it basically made to produce sound to be reverbed, so that can basically be catchy and basically sort of keep the audience alive, right? In the dim lights. So that's how basically reflection and echoes are helpful, and they also used in some music industries to basically produce some good hearing effects over here, right? Hanji, so now the coming to the speed of sound in air and different mediums over here. So I just told you guys in the start that speed of sound in air was around 330 meter per second, right? Is 330 meter per second. So now you can just estimate कि हमारे पास इन लोगों ने roughly ranges दी हुई हैं यहाँ पे हमारे पास, ठीक है? And in what you can see that if the material becomes more dense, let's say if the state changes from gas to liquid, then liquid to solid, ठीक है? You can see that there is a increase in speed here. That speed of sound increases here. Can you explain why? Why does the speed increases if you basically go from state air to gas, sorry, gas to liquid to solid? It has a very simple reasoning here. Can you explain that? Yes, anyone? Can you explain that why is the speed increasing in water as compared to air? Why is the speed increasing in concrete as compared to water? Yes. Give me a guess, at least comment. Hmm. So if you recall the states of matter, how are the particles arranged in the liquid? How are the particles arranged in the air? How are the particles arranged in solid? That's good. ठीक है. What I saying is that particles are arranged pretty far away in air. Yeah, that is the answer, right? So if you just recall the states of matter chapter, ठीक है. So in air, the particles are basically roughly around this. ठीक है. If I go to liquid state, if I go to liquid state, right? So particles sort of are closer to each other, but they can slide over each other freely, right? This is liquid state. Now if I go to solid state, right? It becomes more dense, right? Now, if any single particle vibrates, it moves the entire chain, right? So now, if let's say if a sound wave was produced in a solid, okay, let's say if I basically punch on the wall of my room, so you see the sound almost instantly travels through the wall, right? So why is it? Because when I cause vibration in this particular set of structure, the particles are pretty close to each other and they basically pass on the vibration at a very fast rate, right? Because the particles are pretty close to each other. Now, similarly, if I basically, let's say, produce a sound wave here, okay, so this will basically start to vibrate the particle, but again, they are not so close compared to solid, right? So speed you can see that of a sound in water is around 1400, right? Now, if I go to air, you can see the particles are almost pretty far away from each other, right? So if let's say this particle want to strike this particle it will take some time to reach over there, right? And so on and so forth. That is why the speed of sound in air is around 330 to 350 over here. However, in concrete, the solid state, it has 5,000 meter per second. Steel basically has more number of particles per unit volume. That is why it has more number, greater speed as compared to concrete over here, right? So just one more, one more point over here, that if you basically increase the temperature, the particle is going to vibrate at a very fast rate, and hence it's going to increase the speed also, because number of collisions will start to increase if the temperature is higher over here, right? Right. So the atmospheric pressure do not change any effect in the speed of basically sound. However, only temperature does, right? Okay, so when the temperature is lower, the speed of sound also becomes slower, right? Any idea which you think can be used to basically use how to find speed of sound in air? Yes, Mashal. Mashal, are you here? Mashal is here or not?
Uh,
Mashal is here. Okay.
I think by first, for example, if I'm in a room where there is nothing, it's
Mm-hmm.
empty, and
Mm-hmm.
there obviously there would be an echo there.
Mm-hmm.
So I would find a place with a surface that can reflect the voice back if
Good.
I make a sound.
Mm-hmm.
And after standing a distance in a
Mm-hmm.
distance, I would just measure the distance first
Mm-hmm.
and then make a noise.
Mm-hmm.
And I would then, for the time, to calculate time, I would just have a stopwatch with me. I'll
Good.
just on it and stop at the time when I hear an echo back,
Perfect.
and then use the formula of speed distance
Mm-hmm.
upon time. I think that would be the case.
Perfecto. Okay, that's good. That's good. I guess Mama was on the same track. Okay. So yeah, that's good. That's great, right? So that is what you will do, as Mashal shared the idea with you guys. So let me just draw the diagram here, just to visualize okay, what are you talking about here, right? Let's imagine okay, you are on the fields, right? You are on the fields. Let's say it's a smooth surface, right? And let's say this is a wall, right? Let's say this is a wall here. Okay, convert this is not converting to a shape. Let me fix it now. Let's say it's a wall, it's a huge wall, right? And here nothing surrounding you. It's a, let's say, closed room over here. I'm just showing you the side view from. Okay, this is the side view here of a room. Okay, which has, let's say, some green carpeting over here, and it is also closed from the top. Okay, so now let's say this is Mashal standing here. Okay, so let me just remove this option here. Let's say you have basically Mashal here. She is standing over here. Okay, and she basically is going to use some echo method to find speed of sound, right? And we know that there should be roughly around speed of sound in air should be roughly around equals to 340 meter per second, right? Okay. So now she basically has instruments. She has some instruments basically at her end, and that are as follows. Okay. So she has the following instruments. She has a stopwatch, right? And she has a, let's say, a tape measure. Okay, a tape rule. So a tape rule is basically a scale which can basically be rolled out. If you might have seen in carpet shops, they have a huge tape rule which basically comes out, and you can basically measure huge lengths, right? So let's say she's using that, right? So why? Let me just iterate what each instrument will do. It will measure time. Okay, this instrument will measure time in seconds, and this instrument will basically measure the distance in meters. Right now, what is going to happen? Masha is going to make a sound, right? A sharp sound. Let's say she makes a sound. Let me just make it perfectly. Let me choose another color here, and let me choose this color here. She makes a sound, right? It goes in compressions and reflections, right? And this basically sound does what? It hits the wall in this direction, okay? Then comes back, right? So now let's say Mashal has basically marked the distance from the wall, right? She has marked the distance from the wall where she is standing, okay? And she has measured the length using a tape rule, and that distance is coming out to be D, right? So can anyone tell me that when she's, let's say, made some noise, the sound basically went first here by distance d, then came back after distance d over here, right? So what is the total distance that the sound that the echo has traveled? Let's say if I was starting from Mashal, let's say a particle energy went from Mashal to the wall and then came back. So what is the total distance that the particles basically or that the sound traveled? Yes, Mashal.
So we would multiply the distance by 2, because for the distance when a particle is going from my side to the wall and it is coming back, so it would become 2D.
Good, perfect, right? So it goes by a distance d on the right and comes back by a distance d, right? So it has traveled a total distance of d plus d, that is 2d, right? So we know that the total distance that the echo has traveled, the sound has traveled, that is 2d, right? Now we want to measure one more thing, that is time, right? So as Mashal told you guys, okay, as soon as she basically generates a sound, she will start the stopwatch, right? So that will basically measure T naught, right? And then when she hears back her echo voice, she will basically stop the stopwatch, right? So since the stopwatch started at time equals to 0 seconds, so the T1 would be the time to basically when she will hear the sound. Let's say, let me just make it simple. So the time it takes for Mashal to basically hear back her sound is T seconds, right? Time taken is T seconds. So how can I find speed? If you recall the chapter motion, and which basically topical past paper were you assigned to finish. So what is the formula of speed? We have the distance, we have the time. How do we find speed? Yes, it's going to be the distance upon time, right? Yeah, distance upon time, and the distance over here is twice 2d, right? Over here. And that should basically give you the answer over here. Okay, and this is the experiment which you should know, and you should know the instruments to use. You should know what for what purpose are they going to be used. You should know what readings will you take, okay, distance and time, and then what formula will you apply over here. So this should basically summarize to 6 marks, right? So this is what is written over here, that an estimate of speed of sound in air can be made directly. You stand about 100 meters from a high wall, okay, or building, and clap your hands, right? So then echoes are produced. So when the clapping rate is such that each clap coincides with the echo of the previous one, the clap has traveled to the wall and back in time of 2 claps, okay? And then they are basically summarizing this over here, okay? If you basically produce a sound, and if you know the distance that the sound has traveled in the time when you have noticed using a stopwatch, that's t. So you can basically find estimate of speed of sound in air. That should be roughly around 340 meter per second, right? Theory, if it makes sense, this experiment, give me a raise of hand. Okay, it makes sense to Mema, Mashal, and okay, everyone. That's good. So now we have another experiment which we can use to estimate the speed of sound in air. That is as follows, right? It is basically a direct method here. That is basically using microphones here, right? So if you recall, Microphones are what? Basically, microphones are inside your mobile phones, right? And what are they capturing? They're basically capturing the sound waves, right? So, what is the experiment here? Let's say you have the microphone here. This is a microphone, right? It's a receiver here. And let's say it basically sends signal to a device. Okay, let's say a computer. Okay, let's say it's a computer here. So let's say if there is Hamza here, right? Hamza wants to basically do the experiment on his, let's say, application, right? He made an application to send to test the speed of sound, right? So he basically speaks, right? So what are they saying over here? The speed of sound in air can be found directly by measuring the time taken for a sound to travel past two microphones separated by a distance d here, right? Okay. So now I have this microphone one here, right? This is microphone one here, right? So अब क्या हो रहा है हमारे पास? I have another microphone over here, which is here. Obviously, sound is going to basically travel across this also, and it is again connected to the computer here, right? This is M2, microphone 2. So these waves are going to again cross this particular boundary of the microphone 1, and they're going to basically come forward, right? And we have reflections, and then compressions, and then reflection here, and compression here. And the distance between the separation of these two mics are basically a distance d, right? So the computer will know that Hamza की voice detect हुई है when the microphone one basically detects a signal over here. As soon as the microwave microphone one basically receives a sound signal, it basically tells computer to start the timer. ठीक है? So that basically timer starts. ठीक है? So it measures t naught, that is 0 seconds, and the timer starts. So when the wave hit basically the microphone 2, the timer basically stops. It measures T T2. Okay, let's say that is T. The change in time that basically it took to reach to from microphone 1 to microphone 2 is basically T seconds. Okay, T minus 0 is T. And then you basically can simply use this formula, that is the distance traveled by the sound between microphone 1 to microphone 2, that is distance d, and the time taken, that is t seconds, that the computer measures. You can directly find out the speed of sound in basically air by applying this formula, that is just the speed of sound in air is going to be t upon delta t, right? So this is a direct method over here which is going to give you an approximately accurate answer that can be found using echo method, right? So if it makes sense, give me a thumbs up. It makes sense to Varda. It makes sense to Mashal. That's good. It makes sense to Hamza. Okay, that's good, right? So these are experiments which can pop in your P4 also and then your P2 also, right? Okay, ji. So let's move on and then I'll now learn about some properties of sound, right? Some pitch, what a pitch, what is loudness, and what is a musical note, what is basically a sharp note, so on and so forth, right? Can anyone share an idea about musical, let's say, instrument? When do you know that someone is playing a flute? And when do you know that someone is playing guitar? And when do you know that someone is playing a drum? Can you just share your ideas on that? How can one know which instrument is getting played depending upon the sound? How? Yes, I just want a comment. Yes.
Sir,
Yeah.
so like they are, we can find out by based on their sound waves. Like of course, the tunes they play have musical notes and they have specific frequencies, which is of course measured in hertz. And they in music, it's called also pitchy. Like there are different pitches also. Like different frequencies have different pitches. So this is how we
Yeah.
find out. And
That's good. That is good, right? So, the important points in my response was basically the frequency, right? So every instrument has a different pitch, right? So we'll see okay, what is the pitch over here, right? And then it also depends upon the loudness, right? You can see that the drum sound is pretty loud, right? It makes a dum 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 sound, right? Let's say if you compare a flute, it's pretty sort of soft, right? So we will see that okay, how does that basically these how what are these first of all properties, pitch, loudness, and quality, and how do they contribute to the quality of musical note, right? So what is pitch? So pitch is just the frequency of the sound, right? So if you hear a very sharp instrument playing, let's say a very electric guitar, okay, producing a very sharp note, so that is going to be irritating that the musical is instrument is playing at a very high frequency, right? Let's say if you hear a drum beat over here, thum, 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 then you can see basically the pitch is very low, right? Pitch means okay, the frequency of the sound production, the repetition of the sound beats are very low, right? So again, what is pitch? Pitch is basically the frequency of the sound wave, right? It is the frequency of the sound wave. It comes in your MCQs, okay? So pay attention. ठीक है so the pitch of a note depends upon the frequency of a sound wave reaching the air ठीक है and high pitch has high frequencies and a short wavelength right if you hear a girl let's say shouting with a very sharp noise ठीक है so you basically sometimes start to feel some pain in your ear, right? So why is that? Because the frequency is very loud. Not loud frequency, not loud. Frequency is very high. Okay. So that causes your eardrum to vibrate for very huge amount of times per second, right? So that creates some basically pain in your eardrums. Uh Let's say if there's a biker, right, a motorcyclist who basically have some played with his basically altered his some bike and is producing a very sharp, unpleasant noise. Again, that is producing a very high frequency sound over here, right? An ambulance, right? Ambulance has a very high pitch, so that can reach a longer distance, so that people in front of the ambulance are already alerted in advance, so that they can clear the route, right? You will hear a very short, sort of very sharp noise of ambulance coming in front of in back of you, right? So they have very high pitch that is designed purposefully to basically let the other know that make way for the ambulance, right? So again, what is pitch? Pitch is basically the frequency of the sound wave that is hitting the eardrum, right? Does anyone know what is a tuning fork? What is a tuning fork? It's not the one which you basically use to eat at your homes. Yeah. So it is some, you might have this in your labs. You might have done an experiment in your labs that this teacher basically showed you the spring, the tuning fork over here, and he basically hit across uh surface. So I have a comment from Martha. She says used to make a sound. Not exactly. It is
sound
basically used to
waves in
produce
air,
some. Yes, Amma.
sound waves in air, like when you hit it, it vibrates, both thongs vibrate.
Yeah. So let's say you have a surface here, right? And let's say you have a tuning fork here, right? So when you basically strike it with, let's say this is the ground or a table, let's say just say a hard surface, right? So when you basically hit this sharply with the hard surface, it starts to vibrate, take it back and forth. So the quality of a tuning fork is that it produces a sound note, a sound wave of a single frequency, right? दैट इज अ ब्यूटीफुल नेचर ऑफ इट यहाँ पे इसकी बेसिकली यहाँ पे इसकी ना लेबल हुई होती है कि व्हाट फ्रीक्वेंसी डज इट प्रोड्यूस लेट्स से इट प्रोड्यूस अ फ्रीक्वेंसी ऑफ 100 हर्ट्ज right so you will hear a sound basically coming to your ears of a frequency of 100 hertz and if you try to measure it out using let's say some computers or some electrical instruments, you can basically get the exact value of 100 hertz. So basically a set of tuning forks can produce a frequencies marked on them, okay? And that is going to be exact, right? So what happens? They have two steel prongs, which can be seen over here. One is this, the another one is this. So when you basically stack it with a surface or let's say table, it basically move in and out. Okay, move in and out means ke it moves in and out, right? Both of the steel prongs here, right? And what does it do? It causes the air particles nearby the tuning fork to vibrate, and basically it causes the generation of the sound wave. So any vibrating source is basically a source of sound, right? So that basically produces a frequency, a sound wave with a certain frequency over here, right? Then we have loudness here, right? So if I want to summarize loudness, what is loudness? It is just the amplitude of the sound wave. Amplitude of the sound wave, right? That how much energy does it have, right? Okay, so it is the measure of energy of a wave also, right? Energy of the wave, of the sound wave, right? And a note becomes louder when more sound energy enters our ears per second, right? This will happen when the source is vibrating with a larger amplitude, right? So again, the amplitude is basically the measure of loudness. So if a violin string is strung, is bowed more strongly, or let's say if you have a guitar and if you basically hit the A chord, the thicker one, okay, which produces the loudest note in the guitar. So you will hear very a loud note over here. Okay. If you start from G string with that is the bottom one, okay, the E string over here. So we basically start to see that the bottom one has a very sharp sound. Okay, it has a very high, it is very less loud. And then if we go up, the note becomes louder, right? Why does it become louder? Because the thicker the string, the more amplitude with which it basically start to vibrate, right? So similarly, this is true for violins, right? So if the amplitude of vibration increases, so basically the sound wave amplitude increases over here. The note which you hear basically hear becomes louder because more energy is basically getting transferred from the violin string over here, right? So this is loudness over here, right? So this is let's say if we have a drum, right? Let's say if the drummer is basically beating the drum quietly, okay? Let's say with a smaller with a smaller energy, we start to beat the drum very with a very sort of high amount of energy. You basically start to feel that the note has become louder, right? It's a thum, then thum, right? So that is basically loudness over here, right? Then the third parameter which we have is quality, right? Let's say if we have a very rough instrument, let's say if we have a guitar, which has two broken strings, right? So if you try to play that guitar, it would produce sounds, but with no such good quality. Right? If you can see that we have different instruments, basically sound waves here. The violin is at the bottom. On the top right, you have piano, and on the top left, you have the sine wave that is produced by a tuning fork, right? So ideally, we want the wave to be as sharp and as smooth as possible, like the tuning fork one. But it is the quality of a wave also that represents that what instruments is getting played here, right? So if you have piano, you will see that you will have the top right representation over here. And if you have violin, you will have a bottom sort of wave producer here. So the clearer the sort of the more smoother it is, the clearer will basically be your sound over here. So if you have microphones or speakers in your houses, so they have amplifiers also, right? What are amplifiers? They basically, let's imagine if you have a speaker, if you have a speaker, right? Let me just say this is your mobile phone. This is your mobile phone. And you basically have attached your mobile phone using aux to a speaker, right? Right. And what the speaker does, it produces sound in basically huge, basically large amplitude, right? You can hear very loud music, right? So what is happening inside the speaker is basically your phone sends a very small sort of signal. It is basically in millivolts, right? So your speaker basically amplifies the wave to a huge wave, right? amplifies into, let's say, 5 volts. Okay, then this basically vibrates your the speaker. Okay, it basically causes compressions, to basically generate sound wave, right? But actually, it is the electrical signal which is causing the speaker to vibrate, right? So, what does the speaker inside the speaker? We have a basically the amplifiers over here, which basically also does smoothing, right? It also smooth out the waves which is produced so that you hear very good sound, right? If you have very good speakers in your houses, you hear very good quality sound. If you have, let's say, very old speakers, you might hear some very, let's say, poor noise because the speaker circuitry inside has basically has been damaged, right? And it might be producing this sort of wave, okay? And which might basically produce some undesired sound waves which can be of poor quality, right? So what is quality of a wave? It is that how smooth it is, right? How smooth it is, how much close it is to a sine wave, right? So the smoother the wave, the greater the quality over here, right? So what is quality? Let's start with quality here. The same note on different instruments sound different. Okay. So we say that notes differ in quality. Okay. So quality is also quality in word. Difference arises because no instrument except a tuning fork can or a signal generator, which is basically found in your labs, can produce a pure note here. And then we can basically generate, display these waves of any instrument using a CRO. We will learn CRO in the next chapters, so don't worry about this. So CRO is basically a cathode ray oscilloscope. It basically displays the electrical signals. Okay, if you can see it over here, these are just displayed on the screen of a CRO, right? You will learn that how does it work, how does it produces, how it generates waves here, right? Their different shapes show that while they have same fundamental frequency, their quality differs because they contain additional frequencies here, right? So you can see that in key frequency almost same, right? This is one cycle, this is one cycle, this is one cycle, right? Lambda, lambda, lambda. Similarly, frequency के लिए this is one time period, one time period, one time period, right? You can find frequency from 1 over T. I can see that it is roughly equal, right? Roughly same. So what differs is basically the quality, the shape. And you can see the rough, what is happening over here. So they're saying that they have some additional frequencies added over here, right? So if they are not, if they are of poor quality, they would have additional waves added to the original wave, right? So this is the meaning of quality here, right? So if these three parameters of basically identifying a musical note makes sense, give me a thumbs up quickly. So it makes sense to Hamza, Mashal. Okay, that is good. Varda, is it clear? Okay, that's good. Okay. So we have learned about these properties. So now I'm gonna basically give you a question. Jalli say you have 2 minutes to solve it out. You have given the frequency, given the speed. You want to find the lambda of this wavelength of the sound, right? That is produced at this particular frequency, right? And when you're done, raise your hands. Okay, Ji, so I believe that you should be done. This is just a two-line question. So what are you given over here? You're given the following things. Given the frequency of the sound that is produced right now, that is 256 hertz, right? You're given the frequency of the speed of sound in the air that you all know, that is 340 meter per second, right? You want to find that what wavelength of the wave basically is produced here, right? What is the wavelength of the wave that is produced here? So you want to find lambda. So what is the formula for this? The formula for this is speed is equals to lambda f. And how do you find the lambda? Lambda is going to be speed upon frequency. So your speed in air of sound is 340 and your frequency produces 256. So what is the answer that you're getting? जल्दी से बताएं मुझे. I don't have a calculator right now with me. What is the answer that you're getting for this thing? It should be in meters.
So 1.3 rounded off answer.
Okay, that's good. So getting 1.3 meters, that is the wavelength that is produced for this particular frequency. So it is for the node C, right? Middle C जो basically गिटार का string होता है. So उसके लिए बता रहे हैं ये लोग. Then we have ultrasound. We have already discussed this in the last lecture. So ultrasound is the sound which is basically produced at frequency greater than 20 kilohertz, right? If you recall, the audible range of frequencies between 20 kilo to from 20 to 20 kilohertz, right? And if you go above 20 kilohertz, the sound is called ultrasound, right? The sound is too high to be detected by normal ears, but we can use computers or basically electronical instruments to basically display it on cathode ray oscilloscope, right? This is used in sonar, right? Ultrasound used in sonar application, right? What is sonar? So basically, ships wants to know, okay, what is the distance of the land, the ground that is below it. Okay. So let's say if the ship is moving, it has certain part of it basically sink inside the water. So let's say if there is a cliff inside this, so you should basically not cross it because it would damage the ship, right? So they constantly measure this. Or let's say they also want to see that if there is no submarine of the enemy, okay, if there is a submarine also which can basically attack it. So they also basically want to know what is happening inside this water over here. So they use sonar application here. Sonar basically does what? This is a transmitter of a sonar. It produces a sound wave of frequency greater than 20 kilohertz, right? And it again uses echo method, right? So क्या करता है? It basically measures time. लेट्स से जब उसने वेव भेजी ट्रांसमिट हुई जब स्टार्ट हुई इट वाज टी नॉट इक्वल्स टू 0 seconds and then when the wave hit the ground the land below the sea it came back to the receiver on the ship it basically measured the time taken that was t1 that's it this was t seconds right it knows the speed of sound in water we know the speed of sound in water that is around 1400 meter per second that is fixed we can find the distance basically of land below the ship ठीक है how that speed is equals to distance upon time, delta t. So delta t is the time taken to basically for the wave to come back. That is going to be t minus 0. That is going to be t seconds, right? So if you know basically delta t and if you know the speed of sound in water, you can find the distance below the ship, right? That is going to be speed into change in time and it should be in meters, right? So that's how sonar is used in ships to basically detect the distance below the ship over here. So if it makes sense, give me a thumbs up. It makes sense to Mama. Okay, it makes sense to everyone. That's good, right? Perfect. Acha, this question is a homework. So I have just explained this कैसे करना है. I want the submission basically till 10 p.m. today. ठीक है और till midnight. If I'm going to first of all complain जिसके होमवर्क अभी तक नहीं आया तो अगर उसके बाद भी आपने आज का होमवर्क भी नहीं किया तो you will have one more complaint. So I told you guys to basically follow the deadlines. So I don't want it to be strict, right? So you are forcing me to be strict. So this is due till today is midnight. ठीक है today is मतलब आज की तारीख that is 23 of February. It will take just 30 seconds to solve. ठीक है
सर एक स्लाइड ऊपर
yes पिक्चर ले लिया आपने अभी करना है बट very smart. अच्छा जी then the last slide which is basically this it is also ultrasound if you have heard you might have heard multiple times in medical application here that is used in hospital right. So how is it used? It is basically used to identify some, let's say, issues in your organs, right? And mostly it is used to basically to find how is the baby, right, inside the mother's womb, about the health of the baby, okay, and if there is anything wrong inside or for the baby or not, right? So this is pretty useful, and but again, overexposure of ultrasound is also harmful, right? So they are used for a small certain amount of time, and then the picture is saved in a computer, so that can be showed to the parents, right? It is used to monitor the health and to basically find out what is the basically if it is a male or a female over here, right? And what happens basically, let's say if you have the skin over here, this is the skin of, let's say, of a parent, and what they basically put some gel here, right? They put some gel here, and then they basically put the machine here, right? And this machine is basically connected to a computer, right? And which does the processing part over here, right? सो जेल क्यों लगाते हैं हम जेल इसलिए लगाते हैं ताकि हमारे पास अल्ट्रासाउंड wave completely goes inside the skin so that it does not bounce off and basically go back to surroundings, right? And this computer basically noticed down the basically reflected ultrasound waves which came back from the different parts of the body. Okay. So this is the end of the chapter. I hope it